Okay, so we all know how to find a simple average, right? You add up a list of numbers, you divide, and you're done. But what about finding the average of something that never stops changing? I'm talking about the temperature over a whole day, or a car's speed on the highway. There's no simple list of numbers to add up. Well, that's a calculus problem, and today we are going to crack it. Seriously, think about this. The temperature outside doesn't just jump from 70 to 71 degrees. It flows, it's continuous. If you tried to measure it every single second, you'd end up with over 86,000 data points for just one day. And what if you measured it every millisecond? The problem just becomes infinite. So how on earth do we find one single meaningful average out of all that?
This slide right here, this is the key. It's how we connect what we already know to where we're going. With a basic average, you sum up the numbers, then divide by the count. In calculus, believe it or not, we do the exact same thing. We just use more powerful tools. Instead of summing up a list, we use an integral to sum up a continuous function. And instead of dividing by the count of numbers, we divide by the width of our interval. It's the same logic, just upgraded for an infinite world.
Now, before we get into any formulas that might look a little scary, let's build some intuition first. Honestly, the best way to really get the average value of a function is with a really simple and powerful analogy.
I want you to imagine the graph of our function. You know, with all of its peaks and valleys. Now picture that as the choppy surface of water in a glass tank. The total area underneath that curve, that's the total volume of water in the tank. So what would happen if you just let all that water settle? It would level out to a single flat height, right? Well, that final level height, that's the average value of the function. It's the one value that represents the whole choppy mess.
All right, so with that water tank picture in our heads, let's look at the actual mathematical tool we use to find that level height. And here it is. This is the formula that does all that leveling work for us. I know, it might look a little intense, but let's connect it right back to our water tank. See that long S symbol? That's the integral. That's the part that calculates the total volume of water, the entire area under the curve. And the B minus A on the bottom, that's just the width of our tank. So all we're doing is taking the total volume and dividing it by the width to find that one single level height. That's our average value. It's that simple.
Okay, theory is great and all, but let's see this thing in action. We're going to go back to that original temperature problem and solve it step by step. So here's our function, T of T. It gives us the temperature at any given hour T over a 24-hour period. You can see it starts with a base of 60 degrees, and then it goes up and down with that sine wave. Our mission is to find the single average temperature for the whole day.
We can knock this out with a simple, repeatable three-step plan. This will work every single time. First, we find the width of our interval. Second, we integrate the function to find that total sum. And third, we just divide that sum by the width. That's it. Let's do it.
Step 1 is by far the easiest. We're looking at a 24-hour day, so our interval goes from time 0 to time 24. The width is just the end minus the beginning. 24 minus 0 is, you guessed it, 24. Easy enough? All right, now for the calculus, we need to integrate our temperature function from 0 to 24 hours. This is our summing step. But check this out, there's a fantastic shortcut here. Because that sine wave completes one perfect full cycle over 24 hours, all of its positive bits and negative bits perfectly cancel each other out. So that entire part of the integral, it just goes to 0. It literally disappears. This means we only have to integrate the constant 60, which gives us a grand total of 1440. And finally, step 3. We take our total sum, that 1440, and we divide it by the width of our interval, which was 24. And there it is. 1440 divided by 24 is 60. So after all those fluctuations going up and down all day, the average temperature for the entire day was exactly 60 degrees. Pretty neat, huh? Let's run through a couple more quick examples, just to see how this pattern works for different kinds of functions. This is really going to help lock in the process for you.
Let's apply our three-step plan again. First up, a simple parabola, x squared, from 0 to 3. We integrate to get the area, then we divide by the width of 3. The result, the average value is 3. Okay, next, let's find the average speed for this velocity function, 3t squared, between 1 and 2 seconds. Same process. Integrate to find the total distance traveled, then divide by the time interval of 1 second. The average speed comes out to be 7. See, it's the same reliable pattern. Doesn't matter if we're talking about shapes or speed.
So, after all that, let's boil this all down to the one core idea that unlocks everything we've talked about.
This is it. Right here, this is the big idea that connects a simple everyday average to a powerful calculus average. If you can just remember that integration is just a fancy way of summing everything up and that you have to divide by the interval's width, you've basically mastered the average value of a function.
So you now have this incredible tool for finding the true average of anything that changes continuously. And that leads to a really interesting final thought. What other things in the world that seemed unaverageable before can you now analyze? Maybe the fluctuating pressure inside an engine? Or the daily power consumption of an entire city? The possibilities are actually fascinating. I hope this helps you see the world just a little bit differently. Thanks for joining me.